Module 1, Lecture B, Categories of Built-ins. By the end of this lecture, you will be able to classify common Python 3.12 built-ins into functional categories based on their primary purpose, map real-world programming tasks to appropriate built-in categories for potential solutions, and identify gaps in personal familiarity with specific built-in categories to guide further study. Core data types, basic scalar types. In Python, basic scalar types are simple values that represent single pieces of information and form the basis for more complex data. These include integers for whole numbers, floats for real numbers, complex numbers with real and imaginary parts, booleans for true or false values, and strings for text. Each type has a distinct role, such as counting, measuring, handling logical conditions, or working with written data. Understanding these types helps you see how Python's built-in values match fundamental kinds of information used in computing and in the real world. Scalar types can be grouped by the kinds of questions they answer and the operations they support. Numeric scalars such as integers, floats, and complex numbers are used for quantitative tasks like adding, subtracting, and modeling quantities. For example, in inventory counts, pricing, or advanced models. Booleans support decision-making by answering yes or no questions, such as whether a user is authenticated or a sensor has crossed a threshold. Strings are used for representation and communication, making them suitable for logging events, formatting emails, or building web addresses. Seeing Python's scalar types as distinct categories helps you understand how values are handled and how to choose types effectively. Numeric scalars like integers, floats, and complex numbers are used for precise calculations, while booleans, though based on integers, represent logical states that clarify your code's intent. Strings provide essential tools for working with text, such as in natural language processing or data cleaning. Grouping integers, floats, complex numbers, booleans, and strings as basic scalar types gives you a foundation for building more complex data structures and algorithms in Python. Python code, basic scalar types. We want to introduce the basic scalar types using simple, everyday style examples. In one place, we show integers, floating point numbers, complex numbers, booleans, and strings so learners can see them side by side. By printing both their values and their types, we connect the abstract idea of a data type with the concrete behavior the learner can observe. This helps make the different kinds of scalar data more intuitive and easier to remember. We create an integer variable called item count and set its value to 3, representing a simple number of items. Then we display a message that shows both this value and its data type. By using a function that records the type of the variable, we confirm that item count is stored as an integer. This reinforces how a value and its data type are connected in a program. We use a floating point number to represent the price of an item in dollars, which is a common way to store monetary values in Python. Then we display the price and its data type to confirm that it is stored as a float. This reinforces how Python uses different data types and how we can check both the value and its type. This example creates a complex number to represent electrical impedance using a function that takes 5 as the real part and -2 as the imaginary part. It then prints the value of this complex number and its data type. This demonstrates how Python represents and handles complex numbers, making the abstract idea more concrete by showing the actual output. We create a variable that represents whether an order has been paid and set its value to true, meaning the order is paid. This variable uses the Boolean data type, which can only be true or false. We then display a message that shows both the value of this variable and its data type. This confirms that the variable is a Boolean and that its current state is true. We create a variable to store a customer name and assign it the text value Alex Johnson, which represents the customer in a readable way. Then we display a message that shows this value along with its data type. This confirms that the variable is holding a string as expected. Doing this reinforces how type checking works in Python and helps ensure our data is in the correct format. We create a formatted sentence that combines several values, such as the customer's name, how many items they bought, and the price per item, using a format string that lets us insert these values directly into the text. This makes the sentence dynamic because it automatically reflects the current values of the variables. We then print this summary sentence to the console, along with its data type, to confirm that it is a string. This demonstrates how different scalar values can be combined into one clear, readable string output. This script introduces Python's basic scalar types using simple, real-world examples. It uses an integer for an item count, a float for a price, a complex number for electrical impedance, a Boolean to show whether an order is paid, and a string for a customer's name. Each value is printed along with its type so you can see how the data looks and how Python classifies it. The script then combines all of these values into one formatted summary sentence, showing how different scalar types can work together in a single coherent output. Core collection types. In Python, lists, tuples, and ranges are core collection types that organize group data in different ways. Lists are ordered and can be changed, so they work well for collections that need updates over time. Tuples are also ordered but cannot be changed, which makes them suitable for fixed records, such as stored settings. Ranges represent sequences of integers in a compact form, allowing you to define numeric sequences for tasks like iteration without storing every value. Together, these types support different needs for working with ordered data. In Python, dictionaries and sets extend basic sequences by letting you organize data by meaning rather than position. A dictionary links keys to values so you can quickly look up information using labels, which is useful for things like user profiles or configuration settings. Sets, on the other hand, store only unique elements and are helpful for removing duplicates or finding shared items between groups. Together, these structures support efficient data handling based on keys and membership tests instead of simple indexing. In Python, choosing the right core collection depends on order, mutability, and uniqueness. Lists are ordered and can be changed, so they work well for data that updates over time, while tuples are ordered but fixed, making them better for stable records. Ranges efficiently represent sequences of integers, especially for looping. Dictionaries and sets are designed for fast access. Dictionaries connect keys to values, and sets store unique elements. Understanding these traits helps you manage changing lists, fixed data, iteration, key-based lookups, and collections of unique items effectively. Python code, core collection types. This lesson introduces the main Python collection types using simple, everyday examples and highlights how they differ. It focuses on how each type handles order, whether its contents can be changed, and whether it allows duplicate values. You will compare lists, tuples, ranges, dictionaries, and sets, and hear short summaries that clearly show how each one behaves in terms of ordering, mutability, and uniqueness. A shopping list is stored in a list, which is a mutable collection that can be changed after it is created. The list starts with items such as milk, bread, eggs, and apples. We then add butter using the append operation, showing that the list can grow dynamically. Next, we replace bread with whole wheat bread in the second position, demonstrating that individual elements in a list can be directly updated. In this example, a fixed location is stored using a tuple, which is an immutable data structure. Immutable means that once the tuple is created, its contents cannot be changed. The tuple holds two floating point numbers that represent the latitude and longitude of New York City. Using a tuple in this way helps protect the coordinate values from being accidentally modified, preserving the integrity of the location data. We define a range of aisle numbers in a grocery store that starts at 1 and goes up to, but does not include 6. This means the range represents the sequence of aisle numbers from 1 through 5. Such a range is useful when you want to loop over these aisle numbers or use them for indexing. In practice, it lets you systematically work with aisles 1 to 5 without manually listing each number. We create a dictionary that links item names to their prices in dollars, starting with milk, bread, and eggs. Then we add apples with a price of $5 as a new entry. This shows that dictionaries let us easily add new key and value pairs. Because of this, they are useful when data needs to be updated or expanded over time. We create a set of cart items containing milk, eggs, and cereal. And even though eggs are listed twice, the set keeps only one copy because sets automatically remove duplicates. We then add bread to the set, and it is simply included as another unique item. Because sets are unordered collections, the items do not have a fixed position, but the set always maintains only one of each item. We use a simple example to compare core collection types and how they behave. A list is ordered and can be changed, so it holds the current shopping items. A tuple is also ordered but cannot be changed, making it suitable for fixed home location coordinates. A range is converted to a list to show the sequence of aisle numbers in the store. A dictionary maps item names to their prices, showing key value relationships. And a set shows the unique items in the cart by automatically removing duplicates. This script uses everyday shopping examples to show how core Python collection types behave. A shopping list illustrates a mutable list, where items like butter can be added and bread can be changed to whole wheat bread. A fixed location for New York demonstrates a tuple, which cannot be altered once created. A range represents grocery store aisle numbers as a simple sequence. A dictionary maps item names to prices, such as adding apples with their cost, and a set holds cart items while automatically removing duplicates like repeated eggs. When printed, these structures reveal lists as ordered and changeable, tuples as fixed, ranges as sequences, dictionaries as updated key value mappings, and sets as collections of unique items. Binary data types. In Python, binary data types such as bytes and byte array are used to work with raw byte sequences instead of regular text or numbers. Bytes are immutable, so once created, they cannot be changed, which is useful for secure data like cryptographic keys. Byte array is mutable, meaning its contents can be modified directly, which helps when editing binary files or handling network data. These types are important whenever a program needs to deal with low-level binary information, such as reading binary files or processing encrypted data, and they connect Python's high-level features with system-level operations. The main difference between bytes and byte array is that bytes are immutable, while byte array is mutable. Bytes cannot be changed after they are created, which makes them suitable for data that must stay constant, such as cryptographic keys. In contrast, a byte array can be modified in place, so it works well for tasks that involve frequent updates, like constructing network messages or adjusting file headers. This ability to change a byte array directly can also improve performance by reducing the need to create new objects repeatedly. Binary data types, like bytes and byte array, connect Python's high-level code to the low-level byte representations used by systems and devices. They are essential when working with tasks such as downloading files, parsing binary logs, or communicating with hardware that expects specific byte layouts. These types also integrate closely with standard library tools for compression and encryption. Understanding bytes and byte array as core binary types helps you decide when to handle information as text, numbers, or raw bytes, which is crucial for building reliable Python applications. Python code, binary data types. This lesson introduces Python's binary data types by working with bytes and byte array objects. It highlights that bytes are immutable, meaning their contents cannot be changed after creation, while byte array objects are mutable and can be modified in place. You will see how these binary types differ from regular text strings, especially when reading simple binary content. The focus is on understanding when you are dealing with raw bytes versus human-readable text and how mutability affects what you can do with the data. We create a bytes object by giving it a list of integers where each integer represents an ASCII character. In this example, the numbers correspond to the characters H, I, a space, J, and K, forming a short sequence of text. The resulting bytes object is immutable, meaning its contents cannot be changed after it is created. When we print the bytes object, we see its initial value as a sequence of bytes that represent these ASCII characters. We create a mutable byte array from an existing bytes object so that the sequence of bytes can be changed, unlike the original immutable bytes type. The new byte array is initialized with the same bytes as the original, which correspond to ASCII characters. We then display this byte array to confirm that it starts out identical to the original byte sequence, but can now be modified if needed. In this example, we change the first byte in a byte array to the value 90, which represents the ASCII character Z. This operation shows that byte arrays are mutable, meaning their contents can be modified directly after they are created. After updating the first element, we print the byte array to confirm that the first character has been successfully changed to Z. This example shows that the original bytes object does not change even after you modify the related byte array. When you print the bytes object again, it is exactly the same as before, confirming that it is immutable. In contrast, the byte array can be altered, which means it is mutable. This clearly illustrates the key difference between bytes and byte arrays in how they handle changes to their data. In this example, we convert a bytes object into a text string using ASCII encoding. Each byte is mapped to its corresponding ASCII character. So if the bytes represent valid text, we see a readable string. If some bytes do not map to readable characters, we instead see their raw byte values. This approach helps us interpret binary data that may contain human-readable text. This part of the code shows how to work with binary data using an in-memory bytes object. It creates a binary chunk that combines the ASCII characters A, B, and C with 2 extra bytes, one set to 0 and one set to 255. This demonstrates that you can mix readable text and raw byte values in a single bytes object. The code then prints this chunk so you can see its literal binary representation and how such data is constructed and displayed in Python. This script shows how Python handles binary data using bytes and byte array. It first creates a bytes object from ASCII values for the characters H, I, space, J, K, which cannot be changed once created. It then makes a byte array from the same values, which is mutable, and modifies the first byte to represent the character Z, while the original bytes object stays the same. The script also decodes the bytes object into a regular text string and builds a small binary chunk by combining ASCII characters with raw byte values, illustrating basic binary data manipulation in Python. Functional iteration tools. Core iteration helpers. When you face a programming task that involves looping over data, start by identifying the pattern of iteration you need. For a simple pass through a sequence, a basic loop is enough. If you must know both each item and its position, use a tool that provides the item together with its index. When working with several related data streams at once, choose a helper that steps through them in sync so you get matching values at each iteration. Describing your iteration pattern in plain language first makes it easier to pick the right helper before you start coding. Iteration helpers make it easier to handle common real-world tasks by managing the details of looping for you. For example, when building a grading tool that shows student scores with their ranks, you can use a helper that gives you both the position and the value at the same time. When you need to synchronize data from 2 sources, such as employee lists and access levels, a helper that pairs items from both lists is useful. For analyzing sensor data to spot sudden changes, helpers that group readings together support quick comparison. Overall, these tools let you focus on the problem you are solving instead of the mechanics of iteration. Chaining iteration helpers lets you manage complex workflows more efficiently by combining related sequences and tracking their positions at the same time. For example, when analyzing website traffic, you can align timestamps, page addresses, and user IDs into complete records while keeping their index for reporting. In data cleaning, you can first locate errors with exact indices, then match the corrected data back to its metadata. By matching each stage of a task with the right helper, you reduce manual tracking, keep the process clear, and can easily reuse these patterns in areas like finance or scientific data analysis. Python code, core iteration helpers. This lesson introduces core iteration helpers using simple classroom-style examples. You will see how to perform basic looping, how to loop while keeping track of positions, and how to loop over two lists at the same time. The focus is on beginner-friendly explanations and clear printed output so that each type of loop is easy to follow and understand. By the end, you should recognize these common looping patterns and know when to use each one. We begin with a list of student scores, which holds 4 numerical values representing the performance of different students. This simple collection of numbers will later be used to show how to rank students based on their scores. Because the scores are stored together in one list, it is easy to go through them in order and apply operations such as ranking or sorting. We begin by printing a short message to explain that we are about to show student ranks with their scores using a helper that provides both index and value. We then loop through the list of student scores, and for each score, we obtain its position in the list. We set the starting position to 1, so the first student is ranked first, rather than 0. Inside the loop, we print each student's rank and score, formatting the output so it clearly shows the rank followed by the score in points. We create one list that holds the names of 4 employees in a company, and a second list that holds their corresponding security access levels, such as administrator, user, or guest. These two lists are parallel, meaning the first employee in the name list matches the first access level, the second employee matches the second access level, and so on. This structure lets us easily pair each person with the correct level of access later in the program. We introduce a task where we pair employee names with their access levels and display the results. To do this, we use a function that walks through two lists at the same time, one with names and one with matching access levels. For each position in the lists, we take the name and its corresponding level and print a clear, formatted message. This ensures every employee is correctly matched with the right access level, and the output remains organized and easy to read. We first print a short message to introduce the numbered list of employee records. Then we loop over two lists at the same time, one with employee names and one with their access levels, by pairing their corresponding elements together. We also use a counter that starts at 1 to keep track of each record's position. Inside the loop, we print a formatted line that shows the record number, the employee's name, and the employee's access level. This method efficiently combines numbering and pairing, so each employee's access information is clearly displayed with its position in the list. This script shows how to use basic iteration tools in Python to organize and display list data. It first uses the enumerate function to loop through a list of student scores while keeping track of each student's rank. It then uses the zip function to pair employee names with their access levels so they can be processed together. Finally, it combines enumerate with zip to produce a numbered list of employee records that includes both the name and the access level, demonstrating a clear and structured way to work with multiple related lists. Boolean aggregation basics. When working with sequences in a program, you often need to make a single decision based on many true or false values. Boolean aggregation tools let you combine these values into one result instead of manually looping and tracking flags. Using built-in functions to check whether all or any conditions are met simplifies your code and makes it easier to understand. This is especially useful for tasks like anomaly detection or input validation, where recognizing the problem as Boolean aggregation helps you avoid repetitive logic and write clearer programs. Boolean aggregation is useful when you need a single yes or no answer from many checks, such as validating a web form or a data pipeline. Each field in a form, like email or phone number, has a rule that returns true if it is valid and false if it is not. You then combine these results to decide if the entire form is acceptable, allowing actions like account creation only when all checks pass. The same idea applies in data pipelines, where you might require all quality checks to pass before loading data, or trigger an alert if any critical check fails. In both cases, built-in tools that test whether all or any conditions are met help turn many small decisions into one clear outcome. Boolean aggregation is important for making clear decisions from mixed or uncertain data. It lets you combine many true or false signals, such as whether any delivery vehicle needs urgent attention or whether all meet safety standards. The same idea applies in recommendation systems, where you might check if a user has reacted positively to any item or has completed all required steps for a feature. In all these cases, you are condensing multiple Boolean indicators into a single outcome, and recognizing this pattern helps you use Boolean aggregation tools to turn complex checks into simple, effective operations. Python code, Boolean aggregation basics. We will use simple form field validations to demonstrate how Boolean aggregation works. Instead of manually tracking flags in loops, we can rely on built-in tools that check whether all conditions are met or whether any condition is met. These tools replace verbose logic with concise decisions. This approach connects everyday validation checks with clear, compact Boolean reasoning. We define 3 variables to track whether each field in a shipping form is valid. The email field is marked as valid, the phone field is marked as invalid, and the address field is marked as valid. These validation results will later be combined to decide if the entire form is acceptable overall. We collect the results of each field check, such as email, phone, and address validity, into a single list of true or false values. Grouping these results together makes it easier to evaluate the overall validity of the form. With this structure, we can later use built-in aggregation functions, like those that check if all or any values are true, to quickly determine whether the form as a whole is valid. We use the all function to quickly check whether every field in a form is valid. It takes a list of true or false values, each one coming from a separate validation, such as the email, phone number, or address checks. The function returns true only when every value in that list is true, meaning all fields passed validation. This lets us combine all the individual results in one step instead of manually looping through each field. We use a built-in function that checks whether any item in a collection meets a condition to see if our form has failed validation. A generator expression goes through each field result and tests whether it is not valid. The function then returns true if at least one field is invalid, meaning validation has failed. This lets us efficiently detect any invalid fields without writing explicit loops or managing extra status flags. This code checks whether all fields in a form are valid and then prints a single message with the result. It uses a built-in function that takes a list of true or false values, each representing an individual field check. If every field passes, the overall result is true. Otherwise, it is false. This gives a clear, simple summary of the form's validation status, so you can quickly tell if every field has passed the checks. The code uses the result of a function that checks whether any validation result is false to decide if the form has invalid fields. If at least one field fails validation, it prints a message indicating that there is a problem. This approach provides a simple and clear way to signal that the form contains one or more validation errors. This script shows how to use Boolean aggregation to validate a shipping form. It stores the validity of each field as a list of true or false values, then uses a built-in function to check if all fields are valid, producing an overall true or false result. It also uses another built-in function on the negated values to see if at least one field is invalid. When run, the script prints whether all fields passed and whether any field failed, simplifying validation by avoiding manual tracking of flags. The subheading for the subtopic, sorted and reversed. When working with ordered data, two important operations are sorting and reversing. Sorting arranges items, such as student records, by a chosen field like grades or last names, while reversing flips the order of a sequence. These operations do not change the actual data, but they change how it is organized and viewed. By reshaping sequences in this way, sorting and reversing reveal patterns, support better decisions, and prepare data for tasks like searching or summarizing. When working with data, choose sorting when you need to organize items by a specific property, such as price or hire date, possibly using multiple fields in order of priority. Sorting changes the order to match your chosen criteria. In contrast, use reversing when the data is already in a meaningful order and you simply want to look at it from the opposite direction. For example, you might reverse stock prices or user actions to focus on the most recent entries without changing the original logical order. Sorting and reversing let you change the order of data without changing the data itself, which is useful whenever you need to look at the same information in different ways. Instead of manually rearranging elements, you can rely on these built-in tools to do the work for you. For example, in data analysis, you might sort transactions by amount to find large purchases, then reverse the order to focus on smaller ones, while still preserving the original list. In user interfaces, you can sort messages by priority for display and reverse them for an archive. Using sorting and reversing in this way makes your code clearer, more efficient, and easier to maintain. Python code. The subheading for the subtopic sorted and reversed. Use simple student grade records to show how sorting can organize data into a clear order, such as from lowest to highest grade. Then, use sequences that already have a meaningful order to show how reversing can flip that order when needed. Finally, compare these two approaches to decide whether sorting or reversing better answers different kinds of real-world questions about the data. We create a list called students, where each item in the list is a dictionary that represents one student. Each dictionary has a name entry that stores the student's name as a text value, and a grade entry that stores the student's grade as a whole number. Organizing the data this way makes it easy to work with because we can sort or filter the students based on their names or grades. We begin by announcing that we will show students ordered by their highest grades. To do this, we use a sorting function that arranges the list of students based on their grade, specified through a small helper function that selects the grade value. We set the sorting to work in reverse, so the list is in descending order, with the highest grades first. Finally, we loop through this sorted list and print each student's name and grade, displaying them from highest to lowest. We begin by indicating that the students will be listed in alphabetical order by name. To do this, we create a new list of student records using a sorting function that relies on each student's name as the sorting key. This produces a list where the records are arranged alphabetically. We then go through this sorted list and print each student's name along with their grade, giving a clear alphabetical listing of students and their corresponding grades. We demonstrate how to display a list of registered names in reverse order without changing the original list. First, we define the list of names in their original registration order. Then we use a reversing tool to loop through the list from the last name to the first, printing each one. This shows how to work with a reversed view of a sequence while keeping the underlying data unchanged. This script shows how to sort and reverse lists of student records and names. It first orders students by their grades from highest to lowest to highlight top scores. Then, it rearranges the same students alphabetically by name to demonstrate a different way to organize the data. Finally, it reverses a list of names that represent registration order, showing how to invert a sequence without changing the original list. Together, these steps illustrate practical uses of sorting and reversing, such as organizing by performance or flipping chronological order. Introspection and environment. Object identity and type. In Python, object identity and type answer two related but different questions about an object. Identity is about which specific instance it is in memory, while type is the blueprint that defines what operations are valid for that instance. Two lists can hold the same values but still be different objects with different identities, whereas two variables can refer to the exact same list and therefore share one identity, so changes through one name affect the other. Reflect on whether you usually think in terms of same value or same object, and whether you can clearly explain that difference, because any confusion here means you should spend more time on these built-in concepts. In Python, every object has a type, and that type determines what the object can do, how it works with operators, and how it is displayed. We often rely on this type information without thinking, such as expecting strings to be iterable or integers to support arithmetic. When code behaves in unexpected ways, it is often because our mental model of an object's type does not match its real type. Regularly checking object types, especially when debugging or working with unfamiliar libraries, helps align your understanding with how the code actually behaves. When you feel confused by variables that seem linked or by unexpected changes to your data in Python, it often means you need a clearer understanding of object identity and type. If changing part of a nested structure affects other parts of your program, you may be missing that multiple variables refer to the same underlying object. If library functions act unpredictably with your inputs, you may not be using type information effectively. Noticing these patterns helps you know when to focus on identity and type tools, which will strengthen your confidence and control when writing Python code. Python code, object identity, and type. This section explains the difference between having the same value and being the exact same object in memory. It shows that when multiple variable names refer to a shared mutable object, changing that object through one name also affects the others. To explore this behavior, you use the built-in tools that report an object's type and its unique identity in memory, which helps you see how values, types, and identities relate. We begin by creating two separate lists that both contain the numbers 1, 2, and 3. Although these lists hold the same values, they are different objects stored in different locations in memory. This setup lets us examine how Python distinguishes between object identity, meaning whether two variables refer to the exact same object, and equality, meaning whether two objects simply have the same contents. It shows that objects can look identical while still being distinct entities in memory. When we assign one list variable to another, the new variable does not get its own separate copy of the list. Instead, both variables point to the same list in memory. Because they share this single underlying list, any change made through one variable is immediately visible through the other. In other words, they are just two references to the same data structure. We first compare the two lists to see if their contents are equal, meaning they hold the same values in the same order. Then we check whether they are actually the same object in memory, which asks if both variables refer to the exact same location. In this case, the lists are equal in value, but are still separate objects, so they do not share the same memory identity. In this example, we first check whether two lists are actually the very same object in memory, not just whether they contain the same values. We do this using the identity check, which tests if both names point to the same underlying object. Because one list was directly assigned to the other, they share the same identity and the check returns true. We can then call the function that returns the memory address of an object to confirm that both names have the same identity value, proving they refer to the same object. We add the number 4 to the end of the list called list A, which changes that list directly. Because list C is just another name for the same underlying list, this change also appears in list C automatically. After the append operation, printing list A shows the updated contents. now including the new element at the end. When two variables refer to the same list in memory, changing the list through one variable automatically affects what you see through the other. In this example, both names point to the same underlying list object. After adding the number 4 using the first variable, checking the second variable shows the updated list. This demonstrates that the two variables are simply different labels for the same data, not separate copies. To understand how different objects behave in Python, we can first check the type of a list, which tells us it is a list and reminds us that lists are mutable and have specific identity behavior. We then check the type of the number 42 and see that it is an integer. This comparison between a list and an integer highlights that some objects, like lists, can be changed after they are created, while others, like integers, cannot. Recognizing these differences in mutability and identity helps us predict how each type of object will behave in different situations. This script demonstrates the difference between value equality and object identity in Python. It first creates two separate lists with the same contents and shows that, although their values are equal, they are not the same object in memory. It then creates a second reference to the first list and shows that changing the list through one reference also affects the other, proving they share the same identity. Finally, it uses functions that report an object's type and memory identity for both a list and an integer, highlighting how Python tracks what an object is and where it lives in memory, especially for mutable objects like lists. Measuring size and identity. In Python, it is important to understand both how many elements your data structures contain and whether two names refer to the same underlying object. Built-in tools let you quickly check size and identity, which helps you reason more clearly about how your program behaves. If you rarely use these checks, you may be missing chances to optimize memory usage and to catch subtle bugs. Becoming more familiar with these tools leads to more precise and reliable code. Understanding how many items are in your Python data structures is essential for real work, not just a curiosity. Size information helps you decide how to batch data, track progress, and allocate memory or other resources. It also matters when setting limits on things like uploads, message lengths, or array sizes that influence which algorithms you can use. If you often assume data is small or are surprised when it grows, you may not be using size checks effectively. Building simple scripts that report sizes at key points can help you make these checks a regular part of your workflow. When working with complex, interconnected Python objects, such as those in user interfaces or web backends, it is important to understand object identity. Two variables can hold the same data but still refer to different objects, or several variables can point to the same object, leading to unexpected changes when one is modified. If you are unsure when identity matters more than simple value equality, you likely need a deeper grasp of how Python manages objects in memory. To build this understanding, focus on tracing how objects move through your code and checking which references point to which objects. Python code, measuring size and identity. This section shows how to work with two important built-in tools, one that measures the size of a container and another that checks object identity. You learn to use the length function to find how many elements are in a container, like a list or a string. You also learn to use the identity function to see whether two references point to the exact same object in memory. Finally, you compare values that are equal in content but may or may not share identity, highlighting the difference between having the same value and actually being the same object. We begin by creating a list that stores the lengths of several boxes in inches. This list includes the values 10, 12, 15, and 10. Having these lengths collected in one place makes it easier to work with the box dimensions in later steps. To find how many boxes are in the list of box lengths in inches, we use the built-in length function, which returns the total number of items in the list. This total represents the number of boxes. We then store this value in a variable called box count, so we can easily refer to the total number of boxes later in the program. The program prints how many boxes are in the list by using the list's length, which was already calculated and stored in a variable. This lets the code record the size of the list in a simple, direct way. As a result, the user clearly sees the total number of boxes being tracked. We create two variables that both point to the same list of box lengths, so they share one underlying object in memory. Because they reference the exact same data, any change made through one variable automatically appears when accessed through the other. This setup means the list is truly shared, not copied between the two variables. This example checks whether two variables refer to the same list in memory. It uses a function that returns a unique identifier for each object. By comparing these identifiers, we can see that both variables point to the same underlying list. This demonstrates that they share the same object identity rather than being separate copies. We create a new list called separate boxes that holds the same values as the original list of box lengths in inches, but it is a completely different object in memory. This means the two lists look the same but do not share the same identity. That distinction matters because changing one list will not change the other. In other words, they are independent, so modifications to one do not affect the contents of the other. In this example, we first compare two lists to check whether they contain the same values, which tests for equality. Then, we use a separate check to see whether they are actually the very same object in memory, which tests for identity. The printed results show whether the lists are equal in content and whether they are distinct objects. This demonstrates the important difference in Python between equality of values and identity of objects. When we add the value 20 to the list referenced by shared box A, the change also appears through shared box B, because both boxes point to the same underlying list. This means they do not each have their own separate copy. Instead, they share one mutable object. As a result, any modification made through one reference is visible through all other references to that same object. We first print the shared list after adding a new value to it, and we see that both variables that point to this list show the same updated contents, revealing that they share the same underlying data. Then, we print the separate list, which has the same original values but does not change. This shows that even if two lists start with identical values, they can still be independent objects, and modifying one does not affect the other. This script shows how to measure the size of a list and how object identity works in Python. It first creates a list of box lengths and uses the length function to count how many items are in it. Then it demonstrates that two variables can point to the same list in memory by comparing their identifiers, and contrasts this with a separate list that has the same values but a different identity. Finally, it appends a new value to the shared list and shows that both references see the change, while the separate list does not, highlighting the difference between shared and independent objects in memory. Scope Introspection Basics. Scope introspection in Python is the process of examining where names are defined, such as in a function's local scope, the global module scope, or the built-in namespace. It is important for debugging and for understanding unfamiliar code because it shows which variables and functions are available at any point in a program. Many programmers can write small scripts, but struggle with how names are resolved and how variables change as programs grow and use multiple modules and libraries. Noticing this difficulty is an important first step toward improving your ability to use scope introspection effectively. Python includes built-in tools for scope introspection that let you inspect which names are defined locally inside a function and globally at the module level. These tools expose local and global namespaces as dictionaries, so you can see exactly where each name comes from. Using them helps you avoid guessing about variable origins or relying on scattered print statements. Developers who understand scope introspection can quickly identify visible names, module definitions, and built-in environment names, which makes debugging and code exploration more efficient. If you have ever been confused by which variables are visible in your code, or why a value seems to change unexpectedly, that is a sign you may need to understand scope more clearly. This can happen in situations like data analysis notebooks, where one cell affects another, or in web applications with complex configuration values. Instead of relying on trial and error, you should learn to systematically inspect the current scope and distinguish between local and global names. Practicing Python's scope introspection tools will give you a clearer picture of how your program is structured and behaves at runtime. Python code. Scope introspection basics. This lesson will show how to use basic tools to inspect scope in simple nested functions. You will see how local, global, and built-in names appear using small and easy-to-read dictionaries. The goal is to help you recognize these different scopes and notice any unfamiliar tools so you can practice them more deeply on your own. We define a global variable that stores the length of a board in inches, and it is available to all parts of the program in that module. Any function in the module can read or change this value because it exists at the module level rather than inside a single function. This setup provides a shared baseline measurement that other functions can use or modify. It also illustrates how global scope works in Python, where a value defined once can be accessed throughout the module. We create an outer function to establish a new scope, and inside it, we define a variable that stores an extra length in inches. This variable belongs to the outer function's scope, so it can be used within that function and in any functions defined inside it. However, it cannot be accessed from outside the outer function. This illustrates how variable scope controls where a value can be seen and used in a program. Inside the inner function, we create a variable that represents a small extra board piece, which exists only within that function's local scope. We then display the local variables by listing the keys of the locals dictionary, showing which names are accessible there. After that, we check whether the board length variable is present in the global scope by looking for its name in the globals dictionary. Together, these steps demonstrate how to inspect and compare local and global scopes from within a nested function. Inside the outer function, we first display the local variables that exist at that level so we can see what is defined in its scope. We then call the inner function to examine its own local variables. By doing this, we can compare the inner and outer scopes and observe how the inner function's local scope relates to and interacts with the outer function scope. This example shows how variable scope works in Python using the global variable and nested functions. The program first checks whether a particular variable exists in the global scope by examining the global symbol table and prints the result. It then calls an outer function, which defines its own variable and calls an inner function. Inside the inner function, the code inspects the local scope by listing local variable names, and again checks for the global variable. Together, these steps illustrate the difference between local and global scopes and how variables can be accessed within nested functions. This script uses nested functions to demonstrate how Python handles variable scope. It starts with a global variable for board length. Then the outer function defines an additional length, and the inner function adds a small extra piece. When the code runs, it prints the local variables inside each function to show that every function has its own separate set of variables. It also confirms that the global variable can still be accessed from within both functions. Overall, it illustrates how Python manages which variables are visible in global, outer, and inner scopes. In this lecture, you learned to classify common Python 3.12 built-ins into functional categories based on their primary purpose, map real-world programming tasks to appropriate built-in categories for potential solutions, and identified gaps in personal familiarity with specific built-in categories to guide further study. In the next lecture, Lecture C, we will go over using built-ins effectively. Thank you for your attention. See you all in the next lecture.